Automatic, Addison.
In this tutorial, we will simulate and control a robotic arm in Gazebo. Ever wondered how robotics engineers test their robots without risking expensive hardware? Enter Gazebo, a simulator that lets you test robots in a virtual world before building them in real life. You can work with different types of robots and connect them with ROS2, which means your virtual tests will translate to real robots. This makes Gazebo an important tool when you're developing and perfecting robotics projects. Imagine you want to control a robot, maybe move its arm or make its wheels turn. You need a way for your computer programs to talk to the robot's physical parts, like motors and sensors. This is where ROS2 control comes in. ROS2 control is like a universal translator between your control programs, the software you write, and the robot's physical parts, the hardware. Let's talk about how it all works, starting with where ROS2 control runs. ROS2 control lives on the main computer that controls your robot. This could be a laptop, Raspberry Pi, Intel Nuke, Jetson Orin, or any computer running ROS2. Next, sending commands. So you need to send commands from software to hardware. And how do you do that? Well, you write a program to make the robot move. ROS2 control then takes these commands and it translates them into instructions the robot's hardware can understand. These instructions then go to devices like Arduino boards that directly control the motors. But then you need feedback from the hardware to the software to know what's going on in your precious hardware. And that's where sensors come into play. So the robot's sensors and motors send back information to the computer. For example, motor 1 is currently at 45 degrees, for example. ROS2 control then receives this information and shares it with other ROS2 programs that need it. Let's look at how ROS2 control works with the robotic arm that has 6 degrees of freedom. For example, the MyCobot robotic arms by Elephant Robotics. And what do I mean by 6 degrees of freedom? Well, 6 degrees of freedom means that the robot can move, the robot's arm can move in 6 different ways, just like your human arm. And each degree comes from a motor or joint that enables specific movements, your wrist, your elbow, your shoulder, and so forth. So that's how it works. So you want to pick up a cup. Here's how ROS2 control makes that happen. Let's look at just a standard example, just picking up a cup. So the first stage is your program's command, okay? So you want the arm to move to pick up the cup. Your program, okay, and typically in ROS2, that's going to be move it to, will calculate the positions of each joint, okay? It'll calculate all the positions each joint needs to move through to get the gripper from the starting location to the goal location around the cup. Your program then sends what's called a joint trajectory. Think of it as a list of positions for each joint, okay, in radians, okay? And this joint trajectory gets sent, okay, to the joint trajectory controller, which is part of ROS2 control. For example, it might say, okay, joint 1 should move from 0 to 45 degrees. I'm just using degrees because it's easier to understand than radians, but joint 1 should move from 0 to 45 degrees. Joint 2 should move from 30 degrees to 60 degrees. Joint 3 should go from 20 to 10 and so forth. So that's what happens right here. That's where it all starts, okay? Your program, move it to, will calculate all the positions that each joint needs to go through to get the gripper from the starting location to the goal location, which is right where that cup is. All right, that's called the joint trajectory, list of positions. Okay, and then the second phase of that, ROS2 control comes in. So the joint trajectory controller gets the list of joint positions, okay, the joint trajectory, and the joint trajectory controller knows it needs to smoothly move through these positions, okay, and then it passes the appropriate angle values to what's called the hardware interface. And the hardware interface converts these angles into commands the Arduino or some other microcontroller can understand. The hardware interface sends these commands to the microcontroller many times per second. 50 hertz, 100 hertz, 50 hertz, which is 50 times per second, or 100 hertz, 100 times per second. So now everything is at the Arduino. All the ball is in the Arduino's court. So the Arduino gets these commands through, for example, a USB cable, all right? And the Arduino's responsibility is to control the actual motors in the robot arm. And the Arduino tells each motor exactly how fast and how far to turn. It also reads sensors, we call it encoders, on each motor. This feedback is very important, folks, very important. So Arduino's constantly reading these encoders, these sensors. For example, joint 1 is at 22 degrees, joint 2 is at 45 degrees, joint 3 is at 15 degrees, and so forth. That position information of where the joint it currently is then gets sent back to ROS2 control, all right? ROS2 control shares this with your program, and then your program can check if the arm is moving correctly. So it's a cycle, feedback control cycle. It's a continuous process, and the whole cycle happens many times every second. Your program keeps checking the arm's position. ROS2 control sends updated commands. Arduino keeps moving motors and reading sensors. And then finally, the arm reaches the cup. Okay, keeps doing that cycle again and again and again until the arm reaches all the positions needed to pick up the cup. ROS2 control provides a standard hardware interface. Think of it like a universal adapter between your software and robot hardware. With ROS2 control, you only need to think about where you want the arm to move. You don't need to worry about how to control individual motors. You can just focus on the task at hand, which is picking up the cup, instead of the minute, nitty-gritty details. Beauty of ROS2 control is that it works with different types of arms. You just change the settings, and that's it. You write your program once. You want to switch servo motors to stepper motors, just update a configuration file. So changing from Arduino to a different microcontroller, for example, all you need to do is just update the hardware interface. I shouldn't say all you need to do. It's actually quite complex, but if you want to change to a different microcontroller, you can do that. You update what's called the hardware interface. If you Google ROS2 hardware interface, you can see whole detailed tutorials about how to actually write those. Okay. And your original program will just keep working without the changes, because everything is very modular. You can just swap out components, and the main architecture will stay the same of how the data gets from your computer to the robotic arm and then back up to achieve your objective. And this makes it easier, I don't want to say easy, but easier to share your code with others. So I've got my terminal window open, and let's navigate to the workspace. CD, ROS2, source, my cobot ROS2. It's clear. Okay, and let's create several packages. So the first one we're going to create is the bring up package. So I'm going to do ROS2 pkg create -- build type, and we're going to use ament CMake for the build type. Then they do license BSD 3 clause. Now let's do maintainer name Ubuntu, and then do maintainer email, do automatic Addison@todo.com. Okay, and you can replace the maintainer email with whatever your email address is. And I'm going to do my cobot _ bring up. My cobot _ bring up. So there's the command. Let's press enter. Oh, should do ROS2. Let's Let's go all the way back here. Made a mistake. Another mistake. We need to do build type. There we go. Okay, let's clear. Let's do the up button again, and let's create another package called YAML. All right, and let's create another one. Clear mycobot underscore. Do move it underscore config. Right, it's clear. Now let's do another one. mycobot underscore system tests. Enter. Okay, now let's open the folder here. ROS2 source. mycobot. Here are all our new packages. Okay, let's start by opening up the package XML for the bring up. And let's just fill that puppy in. So find on this line. Okay, and for the description, I'm going to say, oh, X that out. Let's delete this. And I'm going to say, this is where we will hold the launch files and basic nodes for starting mycobot robot drivers. Save. Everything else is fine for now. Let's click that out. Okay, and description, we're good there. Gazebo. Let's open up the package XML for that. Okay, and let's fill this puppy in. And for this one, I'm going to say Gazebo simulation support for mycobot robots, including world and launch files, and then save. Okay, and while we're at it, we've got this open. Let's add a whole bunch of packages that we are going to need for our mycobot application. And I am going to go over here. I have downloaded my whole thing on the GitHub, my whole repo. So we don't need to reinvent the wheel here. Just want to walk everything through bit by bit. Even then, sure, you could clone all this repo to your workspace and run it, but it's good to go through step by step so you understand how I built it up from scratch. So I'm going to copy this block right here under Mint CMake. Let's go. This is in my downloads. I cloned the GitHub repo to my downloads folder, and I'm going to go over here, and we're going to go under CMake and do a Control V and save. All right, it's a bunch of different packages. Now, let me explain what each package is. These are some key packages that we're going to install to handle the integration between ROS2 and Gazebo. All right, so first one, Controller Manager. What is that? Well, that acts like a supervisor for all your robots' ROS2 controllers, making sure they work properly together. We then have the gripper controllers right here, and that package contains a suite of ready-to-use controllers that help you open and close robot grippers. Then on this line, we've got Jazzy messages vendor. All right, that's just some good, useful Gazebo messages. We've got Jazzy ROS2 control right here which is a bridge that lets your simulated robot in Gazebo understand ROS2 control commands. On this line, we've got Python 3 NumPy, and that's a Python package that helps with math calculations for robotics and just math calculations in general. We've got RCL-CPP. You've seen that before. That library has the basic tools you need to write ROS2 programs in C++. We need to make sure we have the ROS-Gazebo library that connects ROS2 with the latest version of Gazebo so they can work together in harmony. We've got the ROS-Gazebo bridge, which helps ROS2 and Gazebo talk to each other by translating their messages. ROS-Gazebo image handles camera images between ROS2 and Gazebo simulation. ROS-Gazebo sim, this is the main package that lets you run robot simulations in Gazebo or a simulation engine. ROS2 control, we absolutely must have. This is the main system that lets you control robots, both real and simulated in ROS2. ROS2 controllers package is a collection of pre-made controllers for common robot movements. Trajectory messages right here. These are messages that tell the robot how to move from point A to point B. We need that. XACRO, you use that in an earlier tutorial. Okay. XACRO, and that's a tool that makes it easier to write and edit URDF files. Okay, so it's URDF macros. All right, and then this last line, Jazzy ROS2 control demos. We'll add some cool ROS2 control demos that are ready-made from this repository. And that is the package XML for that one. Let's save it. Close both of these suckers. Come back here. All right. What other packages? What else? We did the bring up. We did Gazebo. Move it config. Let's open that one up. Oh, sorry. I'm in the downloads folder. Let's go back here. Make sure in the right one. ROS2 source. Cobot ROS2. Move it config. Package XML for move it config. Okay, right now it's totally blank. And we are going to change that. All right. So I'm going to, let's give a description here. I'm going to say this is the move it configuration, launch files, and SRDF. Don't worry about what that is. You'll learn about what that is later. SRDF files for my cobot robots. Okay, and let's just add a description for now. Add in some packages later when we get to move it. Okay, system tests. Let's open that package XML. All right, and let's change the description here. Let's say integration and system tests for verifying my cobot robot functionality, and save. Okay, everything looks good there. Close it out. Okay, and so we've got the bring up we did, the Gazebo folder. Let's go show you that. Gazebo folder, we updated, move it config, system tests. We can't forget the meta package. Let's open that one up. Let's open the package XML for that. And let's make sure we got our new stuff in here. So for exec depend, we're going to add some more packages in here. some of these new packages we just added. Okay, MyCobot. And let's do bring up. Description, Gazebo. Move it config. And then system tests. X that out. Okay, now let's go ahead and open the CMakeLists.txt for the MyCobot Gazebo package. So ROS2 source, MyCobot Gazebo. And let's open up CMakeLists.txt. Right, and we got it open. And let's add some packages. So I'm going to remove this piece here. Okay. And let's start by adding in our requirements. So I'm going to go over here to the downloads. Oh, why do I have two? Okay, let's get rid of that right there. Not sure why that opened. But let's go over to the downloads where we have our repo, downloads, MyCobot, Gazebo. And let's open up CMake. Oh, I'm now going too quickly. Gazebo, CMake. Okay, and so under find dependencies, we've just got a mint CMake right now. I want to add all of these other ones. So I'm going to copy that and let's put it underneath and save. Okay. All of that looks good so far. Make sure you save. X that out, X that out, X that out, and X that out. Open up a terminal window again. Okay, now we need to build the workspace. So let's go to CD, tilde, ROS2, clear, do ROS dep install -I from path src, ROS distro, ROS distro, Y. Okay, we've installed all the required ROS dependencies. And now we're going to do a colcon build. So I'll just show you my alias as I always do. I normally just type build, and what that does is it does CD into the workspace, then it does a colcon build, and then it sources the bash. So that's what we'll do now. Build. Everything built. Voila. Okay, now let's clear. And we'll test the installation. So ROS2 pkg list to grep gz underscore ROS2 control. I keep doing ROS2. Come on, buddy. And there we can see our packages are there. So we do ROS2 package list, and we're looking for the GZ ROS2 control packages. These are the Gazebo ROS2 packages. And now let's run an example. And to run the example, let's do it now. Let's do ROS2 launch ROS GZ sim GZ sim dot launch dot py, and we're going to do GZ underscore args assignment operator. So that's the colon equals quote shapes.sdf. So we're going to launch the shapes.sdf simulation. Let's press enter, see what we get. And this is what you should see. The shapes demo in all of its glory. Okay, so let's Control C. Let's check out another demo. So let's do ROS2, launch, ROS-Gazebo sim demos, and then do joint states.launch.py. So ROS2 launch, ROS-Gazebo sim demos, and then joint states.launch.py. Let's press enter. You can see right here. Another simulation for a very primitive robotic arm. And now when you run each demo, you can see the topics and explore by doing ROS2 topic list. And you can see the different topics right there. All right, so let me just show you something. I'm going to open up Firefox. Let's go to Google. All right, and I want to show you where you can find some other demos. We'll do github.com/gazebo sim/ROS_GZ. Okay. And let's go to ROS-Gazebo sim demos. And on this right here, here's the URL. You can find all the different demos that you can run. Many, many, many different demos. So you're not just limited to the ones that we just did here. All right, let's X that out. Okay. Now let's close that out, Control C. Let's run a gripper example. We can do ROS2 launch Gz_ROS2 control demos, and do gripper mimic joint example effort .launch.py. Okay, so ROS2 launch Gz ROS2 control demos, and then we're going to do the gripper mimic joint example effort.launch.py file. Press enter. Let's see what we get. Okay, so I see we've got an error in here, but it seems to have loaded just fine. Yep. Everything loaded just fine. Okay. There we go. And to close the gripper, let's see if we can get that going. So it's open gripper. Let's do this on the side. Let's see if this works. Used to work in previous versions of ROS2. Let's check it. ROS2 run, and then Gz ROS2 control. And then let's see, actually control demos, and then example gripper. See if this still works. This should, in theory, it should close the gripper. See if it worked. Yeah. You can see the gripper right there, closing. Yep, close the gripper. Okay, now Control C to close. Okay, don't send. It's clear. Now let's try the differential drive mobile robot example. So we're going to do ROS2 launch Jazzy ROS2 control demos. And let's do diff drive example .launch.py. I went by that command really quickly. Let's go back so you can see it. So ROS2 launch Jazzy ROS2 control demos, and then diff drive example.launch.py. Okay, and let's clear. I want you to see the robot. Move that. There it is. All its glory. Use the middle mouse button to kind of move around. You can see the two wheels, caster wheel. Looking nice. Zoom out a little bit. Okay, and how about we take a look at the topics. ROS2, let's go over here. ROS2 topic list. So we see that we have this topic right here, this diff drive base controller command velocity. That should be where we can actually publish a value to move the robot. Let's just confirm that. ROS2, so we're going to do ROS2 topic info diff drive base controller. Oops, CMD val. Okay, so we've got a subscriber, which is definitely our robot, subscribing to velocity commands, twist stamp commands. And we've got no publishers. So let's publish to that so that we can actually move the robot. Okay, remember our robot subscribing to velocity commands of this particular type, geometry, message, twist stamped, and let's move it around. Okay, and the command is going to be, let's clear things out. Paste. Show the command so you can see everything. Okay, try to show it. This is not good. Let's just do Control C. Okay, make it wide first. And here's the command. All right, here's the command. ROS2 topic pub. All right, that's how you start it. Then the topic that you're publishing to, diff drive base controller CMD val, which we saw earlier. The type, message type. Okay, and then the payload, what the message actually is. And that header, we've got a header. We're going to use the current timestamp. We're going to use the base link frame of the robot. We're publishing a twist, a velocity twist command. And the linear component is going to be 0.2 meters per second in the X direction, forward direction. And the angular component, which is how fast the robot space is rotating, is going to be 0.5 radians per second, positive. So 0.5 positive, that is counterclockwise rotation. Counterclockwise rotation at 0.5 radians per second, while we are moving forward at 0.2 meters per second. Okay, and then we have the rate, 5 times a second, 5 hertz. So let's show you the robot here. I'm going to highlight this window on the right, press enter. And now you can see we are publishing. Here we go. 5 times a second sending velocity commands, causing the robot to rotate. All right. Control C. Now to stop the robot, you'll essentially, let's do clear, do the same command, right here and just make everything that's non-zero, 0. So 0, let's go up here, make that 0. Enter. And that should stop it. Yeah, stop the robot. Do Control C. Okay, and let's try to see if this still works in this version. I'm going to try to move the robot using a program. So ROS2 built-in program, Jazzy ROS2 control. Okay, ROS2 run, Jazzy ROS2 control demos. Demos. Okay, and example diff drive. Enter. See, we're driving the robot right there. It's moving. And Control C to close everything. Now we need to create an environment for our simulated robot. So open a terminal window and let's go to the YAML folder. YAML. And let's create some folders. Make dir p worlds launch models. Okay, cd worlds. And let's create our first world. Get it, empty world. Okay. Let's go over here to the downloads, MyCobot. And typically you'll already have a worlds file, or the creator of the particular package will already have a worlds file, but I'll just show you how we would do this. So empty world, I'm just going to Control A all of that and Control V that into my area. Let's save. It's empty world. Make sure you add that code, save the file. Okay. And this file, so this file describes a simulated world using the SDF, simulation description format. And we're using version 1.6. So I'm going to go over here to Google. SDF format key. Simulation. And here you can go to sdfformat.org right here and click on documentation, and you can click on browse and categories. It's got a whole bunch of stuff here where you can just find out more in the documentation about what the different conventions are for SDF, what everything means. Specification, you click the specification tab, it'll walk through what all the tags mean. Okay, we're in the SDF tag, so SDF right here under specification. You can see SDF, and then go back, we've got world tag, and so forth. Got it all. And that'll tell you detailed descriptions of everything. Let's just run through this empty file real quick. So this world right here defines a world named default, and it includes 5 important plugins. Okay, the first plugin we have is the physics system right here, the physics plugin. This is used for simulating physics in our world. We've got user commands. Okay, the user command system plugin. This is for handling user inputs. We then have the scene broadcaster for broadcasting updates to the environment and the scene. We've got to have this sensor system plugin right here to handle sensors like LiDAR or laser range sensor. And we've got our IMU plugin, which enables us to be able to use an inertial measurement unit. All right. Gravity is set to mimic Earth's gravity, 9.8 meters per second squared in the Z. And then we bring in two models into our world from right here. So we've got the sun right here, which provides the light. We bring that in. It's an external model we include. And then we've got the ground plane right here, which gives a flat surface for objects to rest on. And below, right at the bottom, we've got the scene tag, And the scene tag specifies that shadows should not be rendered in this world. So this is the most basic template that we're going to use. It's called empty.world. And this basic template is very good because you can use it to create your own custom world, using this as the foundation and the core. And then you can really build upon it to create your own custom simulated environment for your robots. But this has all of the fundamental elements needed for a functional simulation in Gazebo. Now let's try to launch it. Let's see what happens here. Let's go over. So do a dir. And let's do Jazzy sim. So to launch, here's the syntax. Let's clear. Jazzy sim. All right. And then the name of the world. So I'm going to do empty.world so we can launch it. And there it is, just an empty Gazebo world. Press Control C. Now I'm going to copy over into the same folder. Let's go ROS2, source, MyCobot ROS2, Gazebo worlds. Okay, got empty.world. I'm going to copy over house world and pick and place demo world. Let's paste that into here. And you can see House World starts with the same physics plugins and gravity, but it's got different tags and different components. We've got a ground plane. Then we've got different models that we are bringing in. All right, different models that we're bringing in to our world. Okay, it's everything from chairs to chandeliers to carpet to security camera, coffee tables, everything that you would need for a basic house. And these models came from the Amazon RoboMaker GitHub for the house environment. So I pulled that in. It's open source. Okay, then we've got a pick and place one. We're using a different SDF version, no longer 1.6. We're using 1.7. But we've got all sorts of stuff like a red cylinder object I created, mustard container, Cheez-It box, a bunch of different models. That may or may not be helpful, but for us, it's going to be helpful in our pick and place demo world. There you go. So let's just go back over to the house world. And just explaining, so you need to add models, add these models right here. These models are referenced in here, and we need to add models to the models folder, okay, so that we can load them at runtime. So models is empty right now. I'm going to go over here and actually it's easier. I'm just going to delete the models folder over here in my Cobot Gazebo folder. And let's just go over to the repo Gazebo and copy the entire models and paste it into here. And here are all of the models that we're going to be using in our Gazebo environments. And each one contains a materials and a meshes folder that defines how the model should look in a Gazebo world. So let's see if we can find, let's open this. Let's find the Where is the refrigerator? Okay, refrigerator model. Okay, you can see here, we've got our refrigerator model. Okay, and the name is AWS RoboMaker Residential Refrigerator 1. Okay. And you can see how we define it. It's got a single link, which represents the main body of the refrigerator. I opened up, by the way, the model.sdf file inside the refrigerator model, and it's got a single link, which represents the main body of the refrigerator. And this link has three components. We've got the inertial properties. A mass of 1 unit is specified, which affects how the object behaves in physical simulations. We've got collision right here, the collision tag, very similar to what you've experienced with URDF files. So this defines the shape used for collision detection, and it uses a mesh file named AWS Refrigerator 01 collision.dae. Okay, and this is located in the model's meshes directory, the meshes directory, which is one level up. And remember, the mesh is just a simplified version of the refrigerator's shape used for efficient collision calculations. Then we have the visual tag. This defines how the refrigerator looks in the simulation. It uses a separate mesh file named visual.dae right there. And this mesh is more detailed than the collision mesh used to provide, and it's used to provide a more realistic appearance. Both the collision and the visual meshes are scaled 1 to 1 to 1, meaning they use their original size. So the visual component right here, also you can see here this metadata tag, and specifying it belongs to layer 1, which is used for rendering or interaction purposes in the simulation environment. And finally, the model is set to static, meaning it won't move during the simulation. And this is appropriate for a large appliance like a refrigerator that typically stays in one place. You know, refrigerators don't move. And this structure allows the simulation to efficiently handle both the physical interactions and the visual representation of the refrigerator in a gazebo environment. Okay. Oh, and one other thing I should mention, DAE. What does DAE stand for? That stands for Digital Asset Exchange Files, also known as CALADA, or Collaborative Design Activity Files, and they can be created by various 3D modeling and animation software. The DAE format is widely used in game development, virtual reality, augmented reality, and simulation environments because it's an open standard that can store 3D assets along with their associated metadata. So for this one right here, this particular file was likely created using a 3D modeling software as part of the AWS RoboMaker residential models set. So the modelers would have created both a detailed visual mesh right there and a simplified collision mesh, exporting each as separate DAE files for use in the simulation environment. Let's X that out. The model SDF and model config are typically created manually using just a basic text editor. All right. Now, how can we see this in action? I want to see my house world in action. Let's clear. All right, and we're going to need to do an export so we can tell Gazebo the path to our models. So I'm going to do export this command, Jazzy sim resource path home Ubuntu ROS2 workspace source mycobot ROS2 mycobot Gazebo and then models. Export. Now we launch the Gazebo world. Now be patient. It's a lot of models. It's very heavy. It takes a while to load. And if you're prompted to click wait and do not click forced quit. Do not quit. Just keep waiting for as long as it takes. So Jazzy sim, and then what do we do next? The name of the world, house.world. Take your time. Click wait. Let it come up. Take its time. Sweet old time. And now it is up. Look at that beauty. Look at that beauty. Beautiful house world. Okay, and expand it out so you can see it. You can see our refrigerator there in the back. We've got our sofa in the house, our chandelier. Got a bed over here. Pretty nice. Some chairs, medicine ball. Beautiful looking world. Do Control C. Close everything. And let's take a look at the other world, the pick and place world. GZ, Sim, pick and place demo world. See if this one loads. Should be much faster. Yeah, it is. You can see it moves quicker. There's fewer models, a lot more lightweight. And here we've got a red cylinder and different objects. A box, Cheez-It box, Coke can. There we go. Stuff's kind of flying around. We'll fix that later. Okay, and Control C. Okay, and now let's adjust the height. You saw earlier that we had floating objects in the pick and place world. So let's just make a minor adjustment. I fixed it now. You can see everything now, rather than floating, is level to the ground. Okay, and how did I do that? All right, let's go to Get It, Pick and Place Demo World. And you can see here, what you do is this pose, it's X, Y, Z, and then roll, pitch, yaw. Okay, rotation around X, rotation around Y, and rotation around Z. And what you do, if your objects are floating in the world, appear to be floating, you adjust this Z value. So I adjusted this downwards. So previously on this Cheez-It box, it was 0.17 for the Z value. I changed it down 6 centimeters down to 0.11. For the cardboard box, I lowered it to 0.15 because it was really sitting up very, very high and floating in space. And the Coke can, I changed from 0.15 to 0.0. Save. Okay, now we need to connect Gazebo to ROS2 control. So the first step is to create a YAML configuration file for the controller manager. So that's what we need to do now. And what this YAML file will do is it will tell ROS2 control how to manage our robot's movement in the virtual world we created in Gazebo. So this configuration file will define how our robot's joints should be controlled. Think of it as like a bridge between Gazebo and ROS2 control that defines what parts of your robot can move, how they're allowed to move, and how to report back the robot's current state. So let's just dive into it, and you'll see what we're going to do as we learn by doing. So cd ROS2 workspace source mycobot ROS2 mycobot move it configuration file. Let's do a make dir p config / mycobot _ 280. Okay, that's the new folder we're going to create. Let's go inside that folder, cd config, cd mycobot 280. All right, this is a directory we're in now, a new one we just created. And let's create a new file. By convention, it's called ROS2 _ controllers.yaml. And here is our ROS2 controllers. All right, Let's go over here to the repository that we downloaded off of GitHub. Let's find the ROS2 controllers.yaml. We're going to copy it. We're going to go back over here to the blank file and let's paste. Okay. Don't be intimidated of this file. I make a lot of comments so you can understand what's going on. So what this file is, you can think of it as a manual, okay? Again, that tells what parts of your robot can move. We have the joints, okay? How they're allowed to move, and how to report back the robot's current state. So we've got up here, we've got how often the controller should update. Right here, we've got 100 Hertz. We show which joints of the robotic arm can actually move, how the joints can move with the command interface. It can be position, you could have velocity. And then we have what kind of feedback the system should provide with the state interface. All right, and in this case, we're going to report back the position of the joint, and that's going to be in radians. So this configuration file is essential because it ensures your simulated robot behaves similarly to how a real robot would respond to commands. So let's save the file, close it out, close it out, close it out. All right, let's see what we got in here. ROS2 controllers.yaml. Now let's add another file. Let's add another file right now. We're going to call this one getIt ROS2 controllers underscore template.yaml. Here's our new file right here. Totally blank. And why do we need this template? Well, we want to make sure that our system is flexible to handle different situations like a dual arm robot. Imagine if we had a dual arm robot. Each joint right now is, I'll go back to the file so you can see it. ROS2 controllers. So you see each joint right now has no prefix. You know, prefix, I mean right, link 1 to link 2, left, link 1 to link 2, to stand for a dual arm robot. You know, we want to be able to add some more flexibility to be able to handle a case where we have a left or a right arm that we want to control. In our case, we just have a single robotic arm, so we don't need to use the prefix, but I'm just going to add that in so you can see how you would do that in another use case in case you had a prefix. So I'm going to add the template here. Let's go to the template. Let's copy. Let's go back over here. Sure, we could also copy over the file as well, but I just want you to see this from scratch. That's why we're doing this manual copy paste. So here we have the template, and you can see the difference between the ROS2 controllers.yaml is now we actually have a prefix. So we can, from a launch file, insert a prefix like left or right to stand for the left and right arms respectively. And let's save that and close. Close out everything. Clear. Okay, we are still in the mycobot move it config package, config folder, mycobot 280. And right now I want to go to the CMakeLists.txt within the new move it config package. Okay, CMakeLists.txt right there. All right, and let's update it. Okay. Let's do a getIt CMake. And here it is right now. All right, and we need to add in some lines. So I'm going to get rid of this line. Okay, and we need to, let's just double check what folders we have in here at this stage. It's ROS2 source, mycobot. mycobot move it config. Okay, right now we just have to handle the config folder. So let's do that. Okay, so on this line right here, I'm going to go ahead and put this code. Okay, so let's take away that. We don't have launch yet. Okay, let's just confirm. No launch yet. Yeah. Okay, so it doesn't hurt actually at this stage. Let's just go open and let's create a launch folder. So we'll need that later. Make dir launch. Okay, and let this then add that to our CMakeLists. So you need this block of code. Make sure you add this block of code to your CMakeLists.txt. Okay. And right now we only have one dependency. We're going to change that later, but just keep it like that for now. Okay, and save. All right. Okay, now that we've got that, let's run a clear. And let's go over here, cd ... cd my cobot description, launch. Let's open robot state publisher.py and go to the very bottom. You see, I want to show you this up here. So you see that up here at the top, we've got this process ROS2 controllers config method. What this does, it handles the prefix replacement right here. So it takes the whatever you enter in. When you run this launch file, if you want your own prefix, you can add it as a launch configuration variable. So you can do like ROS2 launch, my cobot description, and then robot state launch, state publisher.launch.py. And you can pin to that a particular launch configuration prefix. So a prefix, you can add a prefix. So prefix equal left, and you can run it, and then it'll insert the prefix like for the left arm or for the right arm. But we're just going to use the default, which is nothing. But that's what this block does, is it then replaces whatever the prefix you added in when you launched it. It replaces that in the ROS2 controllers template and then overwrites your ROS2 controllers.yaml. And we assume in this case our prefix default is just nothing, just no value at all. But right now, earlier we had commented out that block. Now that we've got the appropriate YAML file, we can uncomment that piece right there on line 222. Just uncomment this line which says ld.addAction, opaque function, process ROS2 controllers config, save. Okay, now I think it's a good time to just step back and let's go back to the all-important configuration file. My cobot cd, my cobot ROS2 config. Okay, move it config, clear. All right, let's go to cd config. I don't know why. Let's just delete. Sorry, I'm going to delete this template here. Should not be there. Okay. So here's how your mycobot move it config should look like right now. Should just have this at this stage. Let's move into the config folder. cd mycobot 280. Okay. And let's do get it ROS2 controllers.yaml. Okay, and let's just take a step back and let me just explain what each piece of this YAML file is. So first, we've got the controller manager. The controller manager acts as the central orchestrator. This runs again at 100 Hertz, and it manages multiple controllers simultaneously. This high update rate that we have here, this 100 Hertz, 100 times per second, it ensures smooth motion control and responsive behavior of the robotic arm. Now we've got the arm controller right here, which you can see here. And we've got the joint trajectory controller, which is the type of this particular arm controller that we're using. The controller handles the coordinated movement of the robot's 6-axis arm, 6 degree of freedom arm. It uses the joint trajectory controller implementation, which means it can process complex movement paths while maintaining synchronization between the robot's joints. See that right here. And you can see here that we've set open loop control to false. And what that means is that the controller is going to operate in closed loop mode, which means that it will use position feedback to ensure accurate movement of the arm. And that's key, folks. When you're trying to do a pick and place task, you want that feedback for where the joints are actually currently located in radians. You want that feedback loop. So make sure you have open loop control to false. Okay, and here the arm controller, we have 6 joints connecting from link 1 through the flange link right here. Each joint accepts position commands and reports back its current position state. And the controller supports trajectory integration, meaning it can calculate right here, meaning it can calculate the required velocities and accelerations from position-only commands, and it allows for trajectories that end with non-zero velocities. Now onto the gripper controller. Here's the gripper controller, and the gripper uses you can see right here, you had the joint that we're controlling is the gripper controller. Okay, and we've got different tolerances, goal tolerance, max effort, if we will allow the gripper to stall timeout, and so forth. Lots of different variables that you can use for this. So the stall detection is a cool one because what it's saying is that if movement right here falls below 0.001 units per second for more than 1 second, you know, that's where you want to be able to detect if there's stalls or not. So that's pretty neat too. Got our joint state broadcaster there, and this component publishes the real-time state of all joints to the ROS2's joint states topic. So that enables other nodes in the system to monitor the robot's current configuration. And this is important for tasks like collision checking, visualization, and coordinated motion planning. The template file, let's go over here to the template file. So this template file enables parameter substitution indicated by the prefix to allow for flexible naming, as I said earlier, you know, left or right joint. So it's particularly useful when you want to deploy the same configuration across different robot instances or configurations. Now, each controller is defined with specific interfaces for commands and state feedback right there. And this is the clear contract for how the controller interacts with the hardware layer for the robot. Okay, let's move to the next step. Next, we need to create the XACRO URDF file to handle ROS2 control. So we need to add 2 essential files that bridge Gazebo simulation with ROS2 control. And these files will work alongside your controller configuration YAML to create a complete control system. So let's start by creating the first file. So cd ROS2 source, mycobot ROS2, mycobot description, URDF. And let's create a new directory. Let's see what's in here first. Okay, control. So we've already got control. All right, so let's go cd control. Okay, and let's create the first file. I'm going to do get it, and let's do gazebo underscore sim underscore ROS2 underscore control control.urdf.xacro. Okay. And I need to find this code. Let's go over here to our downloads where we put in the GitHub repository. Let's go to the description. Let's go to the URDF folder, control. And I'm going to take all of that, copy it, and let's put it into our empty space and save. Close it. Okay, here is our file. You can see we are referencing our ROS2 controllers.yaml. Okay, let's close it. See if it's in there. Okay, and so just to explain what that file is. So let's just open it up again. So this file, what it does, this Gazebo sim ROS2 control.urdf.xacro, it loads the Gazebo ROS2 control plugin right here. Okay. Then points the Gazebo to your controller settings file. Okay. And then make sure ROS2 and Gazebo can communicate properly. So you can think of this file like a middleman between Gazebo and ROS2 control. So without this file, Gazebo wouldn't know to even accept commands from ROS2. All right, close it. Now let's create the second file. So get it, my cobot _280 _ROS2 control.urdf.xacro. Let's make sure the name is right. My cobot 280 ROS2 control.urdf. Is that a dot there? Yeah, .urdf.xacro. Okay, and let's just check and confirm. Yeah, .urdf.xacro. Okay, and let's just go over here again. Yeah, folks, you can copy and paste it over, but we're going through this slowly and smoothly so we can explain everything one by one. So I'm going to open this up, Control A, Control C, and then Control V over here and save. All right, let's close that out. Okay, so what does this file do? What does this file do? This file right here is, think of it as the main robot control instruction manual. It sets up two important interfaces for each joint. You can see that right here. At each joint, we've got the command interface. So that tells us how do you send desired angles to each joint. So like move this joint 45 degrees, move this 90 degrees. Obviously, everything is in radians here, but I'm talking about degrees because it's more intuitive. And then we've got our state interface for the position. So this tells us how you read back what angle each joint is currently at. And all of this defines the safe movement limits for each joint. Okay. That's what we get here. So this, you can think of this as defining what each part can do of the robot and how it can do it. That's what that file does. And now you save it and close. Okay, now let's bring it all together into our full robot URDF. So we're going to go to, we're in here in the My Cobot ROS2, My Cobot description URDF folder. Let's go inside the robots folder. All right, and let's open this My Cobot 280.xacro. Okay, and you see we're not importing or including our important ROS2 control pieces. So what I'm going to do now is let's add this first block Okay, so underneath here, this arg use gripper, all right, line 39, I want you to go to line 51 and add this block. Add this block. So include file name, mycobot description, URDF, control, gazebo sim ROS2 control.urdf.chacro, the robot name, and then the use gazebo. Okay, so we're including the URDF file we created that connects ROS2 control to gazebo, and then we're loading the gazebo sim ROS2 control plugin, the XACRO. Okay, the plugin that we defined inside this file right here. Next, we need to include the other XACRO file that we created that tells the system how the joints are controlled and the state and command interfaces. So that was this file right here, this mycobot 280 ROS2 control.xacro file. Yeah, that's this file. And we need to activate that macros that we defined in that file. And that's right here. Flange link use gazebo, mycobot ROS2 control. So including it and then activate it and then save. Okay, now it's time to create the launch file. So let's close this out. Got our XACRO files up. And let's see. Let's go over to the CD 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 mycobot move it config. Okay, we're in here. Let's create we already have our launch folder, so that's good. And we will create a launch folder inside the mycobot move it config launch folder. And let's create the file now. Get it. Load underscore ROS2 underscore controllers dot launch dot py. Good name. Load ROS2 controllers dot launch dot py. Open it up. All right, I'm going to go back over here. Let's go to the folder of the same name. Open it up. Control C, copy and paste. Okay, so these load the ROS2 controllers. Okay, and let's save that file. You can see it's loading the joint state broadcaster and the ARM controller, which were both defined inside the YAML file, and then delayed start. Okay, we did the delayed start so we can launch our controllers with a delay, not all at once. Everything comes up cleanly. Let's close it. Okay, launch file is good. Just make sure our CMakeLists.txt is also updated. Get it, CMake. Yep, got config and launch. Close. Let's clear. Now let's add another launch file. Let's go into CD, mycobot gazebo, launch. We're in here. Okay, and let's do another file called get it. Okay, we're going to call it mycobot.gazebo. Let's see. Let's do mycobot.gazebo.launch.py. Okay. And let's add this code over here. Go back to downloads, mycobot, gazebo. Yeah. So control A, Control C, and let's put this puppy into here. This launches the gazebo simulation with the robot. Everything looking good. Okay, save and close. Okay, now let's create a bash script for quick launching. Let's clear this out. And for our launch, we're going to go into the CD MyCobot bring up folder. And let's go in here. Let's make dir scripts. We're in CD scripts inside the scripts folder that we just created. And let's create a bash file called, let's do get it, mycobot 280 gazebo.sh. Go here and let's take a look. Bring up scripts. Let's add all of this and let's copy it. Okay, and let's place it in our new down here. So this is a single script that will launch the MyCobot robot with Gazebo and the ROS2 controllers. You can see we are launching our, right here, our launch file that we just created. Okay, and we're going to launch it with a pick and place demo world. Let's close. Save it and close it. Let's close all of this. Okay, and now let's make it executable. And to make it executable, you remember from our Linux tutorials, we do this: sudo change mod plus x, and then mycobot 280 gazebo.sh. Type in the password. Okay, I typed LSLA, and you can see it's all good for read, write, and execute permissions, which is exactly what we wanted. Let's now add an alias to quick launch everything, so we don't have to type in a long command to run that bash script. And to do that, we need to add this command. I'm going to do this now. So here's the command. This is the command that you should type in now. So echo alias robot. Okay, it's going to be the robot command. Then the assignment operator, and then a single quote, and then bash, and then the path to the bash script that you just put. And then we're going to put that in the bash RC file. Okay, and then we're going to source the bash to update everything. Enter. And let's just check the alias right now. We can see we now have this new alias called robot, which will automatically launch Gazebo, ROS2 controllers, and our robotic arm. And because we just added a new folder, we need to update CMakeLists.txt. Let's do that now. Okay, let's kind of get rid of that piece. We don't need it. And now let's add a block in here. See, we added the scripts block right there because we just added that new scripts folder. Okay, you can save, close. And now let's update CMakeLists.txt again for the MyCobot Gazebo. MyCobot Gazebo. We're in. And then get it CMakeList.txt. Let's take a look and make sure we've got it all. Oh, yeah. Okay, let's just go here to home. I just want to see all the folders that we've got in there just to double check. Okay, we've got a folder called Launch Models and Worlds that definitely need to be added in here into the CMakeLists.txt so that everything can be recognized properly. So we've got to add the block right now. Let's do it. Let's do it below XACRO. We're going to add it on line 18. So add this block right here. Copy necessary files to designated locations in the project. So install, config, folder, launch, models, and world. Just take a moment and just add that inside the CMakeList.txt. Take your time. Save and close. Okay, before I forget, let's go back to, we're in the workspace. Let's go to CD MyCobot ROS2. Go to CD MyCobot Gazebo. Okay, we're in here now, and let's see, we are missing, let's just check our CMake list again. Okay, config, the config folder. So we need to actually create that directory, make dir config. And you can just see it, dir config, we've got it, clear. Okay, and let's add a YAML file called ROS-Bridge. This will bridge make sure that the time is synchronized between both ROS2 and Gazebo. So clear CD MyCobot ROS2, CD MyCobot Gazebo, CD config. Okay, and let's do get it. ROS-Gz bridge.yaml. So get it ROS_GZ_bridge.yaml. Okay, we're going to go over here, downloads. Gazebo config. Let's open it up. Control A, Control C. And where is our blank file? Control V, save. This will bridge the clock configuration from Gazebo to ROS, making sure the time is in sync. This other stuff, camera depth and camera depth color points, we will cover later. Okay, let's build the package once more using the build alias. And remember, let's go take a look at the build alias again. Build alias, you cd into Workspace, then you run a colcon build, and then source the bash rc. So you can copy this whole command too, just so you can see how it works. Copy the whole thing and enter. Does the exact same thing. I just don't like typing all that stuff every time. And clear. Now, for the moment you've been waiting for, time to launch everything and move the arm. And since we've got an alias here called robot that does this entire command and launches this batch script for us, all we need to do is let's just clear. We don't have to clear, I just like a clean terminal. And let's type robot to launch it all. Be patient while everything loads. Check the logs. Okay, the ARM controller loaded successfully and the gripper action controller loaded. That's all we need to be able to control our ARM. Let's take a look here at RViz. You can see our robotic arm here. Looking good, looking good, looking good. Very nice. Okay, and let's go over to Gazebo. All right, zoom in so you can see it a little bit better. It's moving a bit slow. Okay, and there we go. There we go, folks. Let's make that bigger so you can see everything. Got our Cheez-It box, our mustard container, our Coca-Cola can, our big cardboard box. It's a red pole that'll come into action in future tutorials. We'll be doing pick and place task with that. All right, and then we have our robotic arm right here. Very nice. I do notice the robotic arm is floating a little bit. We can fix that in the bash script. Okay, let's go over here and let's see why our robotic arm is floating like that. Let's go have a look. Right, let's go over here to the terminal. Let's open a new one. Let's go to our bash script. So cd source, cd my cobot ROS2, cd my cobot gazebo. Let's go into the, it's actually in bring up. It's clear, cd my cobot bring up, cd scripts, and let's open this up. My cobot 280 gazebo.sh, and let's change this Z value from 0.05 to 0. Why don't we try that? Let's save it. Okay, and let's close everything down, and we're going to need to relaunch, build, and then relaunch. Let it close. Let's do a build. Do a clear, and let's relaunch, and let's see if our robotic arm has come back down to Earth. Not floating, levitating. Let's check it out. Zoom in. Now it's kind of underneath, which is not cool. All right, so now it's kind of in the Earth. So let's try another one. Let's go back to it. And maybe we need to do something like 0.03. Oops. Let's open it again. And maybe we need to raise it a little bit, 3 centimeters. Save. Let's build again and run. Build. Clear. Robot command to run. Now let's check. Zoom in again. It's almost there. Yeah, let's see. It's pretty good. You can see the base right there. That's a good one. 3 centimeters. Nice and firm in the ground, not levitating. We think we can stick with that. Okay. Yeah, it's a good one. And for different environments, you might need to change and tweak that Z value a little bit, because different environments, I have noticed, like the house world and other worlds that you're working with, might have different ground planes that might be higher or lower. And so if it's higher, you want to increase the Z value, the starting Z value on the robotic arm, just like I did there in the bash script. But this looks okay. If it's any issues down the road, we'll fix it. But for now, it looks pretty good. Everything looks very nice. Let's expand it out so you can see everything. And let's zoom out so you can see the whole world. Use the middle mouse button and twist. Middle mouse button. Okay, that enables you to change the orientation of the scene. And you can zoom in and zoom out also using the middle mouse button. And then I use the left mouse button here to move position left and right. Middle mouse to change orientation, the rotation in the scene. But that looks pretty good. All right, and let's go into a new terminal. Let's see the active gazebo topics. Clear. type Jazzy topic space hyphen L. Okay, and that gets us our topics, active topics. To see the options, Gazebo options, we do Jazzy topic and then help. Jazzy topic, it's 2. Is it 2? Yeah. Okay, 2 hyphens for the help. Okay. And you can see the different options there. See there, help. Okay, let's clear. Now let's see the active ROS2 controllers. ROS2 control list controllers. Enter. And you can see we've got 2 active controllers right there. And so the gripper action controller, which we defined in that YAML file, you remember. And we've got our ARM controller, which we also defined in the YAML file, and our joint state broadcaster, which is broadcasting the state of each joint. Now, if we want to get nitty-gritty detail, we can do the ROS2 list controllers, that same command, space, and then -v to get verbose output. A little bit more detail, give you a little bit more detail for each situation. So we can see the gripper action controller, we see the state interfaces, all right, with the position, velocity, and we can see the command interfaces. We can send position commands, all right, to the gripper action controller that controls the gripper. This controls the robotic arm. We've got our list of joints that can be controlled and the command interfaces, and the list of joints which are reporting data, the position information, and the state interfaces. And then we've got the joint state broadcaster, which is broadcasting the state of each joint out to the ROS2 system for use with other programs, use by other programs. Clear. All right, now let's go back and take a look at the robotic arm. Let's do a nice little aerial view. And you can see right now how our robotic arm, the gripper, is open. How do we close the gripper? How do we close the gripper? Now, to close the gripper, you're going to go into a terminal window, all right, any terminal window, and type this command. ROS2 action. Let's start from the beginning. ROS2 action, send goal, and you're going to do it to the gripper action controller, gripper command, and then we're going to do a control message, a gripper command control message right there, and then send the actual command, okay? And to do the command right here to close the gripper, we have to send this -0.7. That -0.7, that's just a hard-coded value. I just know that because that's what closes the gripper, and it's going to be different for different grippers. And here we have our max effort. You don't need to worry about that. Just keep it at 5. And let's see if we can show both at the same time. The terminal and the gripper closing. So I'm going to enter, and you can see the gripper closed. And in the terminal, you can see the goal finish with status succeeded. And the result, we got the resulting gripper position, -0.69. Okay, which is the goal position for the gripper. And if we want to open the gripper again, we need to send a 0 command, which is, all right, it's just clear. And you can see the only thing that changes here is we change that -0.7 to 0. 0 means open. So I'm going to go over here and let's click enter. And you can see it opened, wobbled a little bit, but it did open, and it finished with status succeeded. Now, how do we deactivate the gripper action controller? Maybe you just don't, you just want to deactivate the gripper action controller. So we'll do ROS2 control set controller state. Okay, and then gripper action controller. Okay, and then inactive. successfully deactivated the gripper action controller. All right, that's just a command. If you just want to deactivate it, you can also, let's see if this, yeah, so active, we'll activate it again. And let's do ROS2 control to see a list of the commands that you can send. All right, clear it. And what else can I show you? So how about we list all the available hardware components that are loaded and ready to be used by the ROS2 controller manager. ROS2 control, list hardware components. And here we are. These are the different hardware components. In this case, it's in Gazebo because we're doing simulation, but these are loaded and ready to be used by the ROS2 controller manager. Okay, now we're just going to clear everything out and let's take a look at our topics, ROS2 topic list. Okay, and you can see the list of topics. ARM controller joint trajectory. This can actually receive a joint trajectory, a list of positions for each joint and move the arm. Okay, and let's do ROS2 action list. Let's see what the active actions are. So we've got 2 active actions, ARM controller follow joint trajectory and gripper action controller gripper command. And later in a future tutorial, I'll cover more in depth about how ROS2 actions work. But ROS2 actions can enable you to send specific goals and you get feedback when this goal is being processed, and then you get the result when it is done. So it's a way to make things happen. ROS2 action, very fundamental concept, which we'll go more in depth to, but this is exactly how we want to use this particular action to actually move the arm from an initial location to a goal location. So let's get ready to do that now. All right, let's clear. All right, and let's go back here. Everything's go here. Just check. Arm is in good shape. Okay, and let's see. Let's type this command to move the arm. I'm going to show you here. Okay, and this is a command. This is the command. Big, nasty command. Don't be intimidated. So ROS2 action send goal, because we want to send the robotic arm to a goal. We're going to use the ARM controller follow joint trajectory action, which you saw earlier when I did the ROS2 action list. All right, show that again. ROS2 action list. We want to use this action move the arm. Okay, and we want to use this action right here. ARM controller follow joint trajectory. ARM controller follow joint trajectory. By the way, just in case before we go through all of that, you want to learn right now in case you're curious. No need to do this now, but just show you. Let's go to ROS2. I'm in the Google ROS2 action commands. And let's do, see what we get here. Understanding actions. Right here, you got a whole bunch of stuff right here. Different commands. ROS2 action list is what we used. Okay, right there. All right, and let's go over here. So if you go over here, we got ROS2 action info. Let's go back over there. So ROS2 action info, ARM controller. Okay, and we see that we have a server called ARM controller, and that's what we defined. If you remember that, we defined that in the YAML file. So we have a server. This is serving. This is ready to serve. Okay, it's ready to process goal actions, which is moving the robotic arm from an initial location to a goal location. But we don't have any clients yet. Okay, we don't have any clients yet. So we have nobody actually sending the goals, a client that's requesting service from the action server to, hey, I want to send the goal from the robotic arm from location A to location B. And so now to create a client here on the command line, you do it just like this. So ROS2 action send goal, ARM controller follow joint trajectory. Okay. the type of the action, and then the actual trajectory. And we've got all the different joint names and the positions that where we want to send the robotic arm to. And then how long it should take, in this case, 3 seconds. All right, and let's get everything ready to go so you can see it. With the terminal on the side, I'm going to click enter, and the robotic arm should move. Goal accepted. It's processing. Succeeded. And you can see here, successful, goal successfully reached, succeeded. Okay, and how do we move the robotic arm back to the home location? We send another goal. Send another goal. Let's clear. But we need to make all of the joint positions 0. 0, 0, 0, 0, 0, 0. And we're going to take 1.5 seconds to do it. Enter. And you can see the robotic arm moving back to the home location. Status succeeded. Clear. Go back to the workspace. And clear. Okay, let's close everything out. Control C. Okay, let everything clean up. Don't send. Let's X that out. Close everything. Let's just start with the blank terminal. So right now we are going to move the robotic arm using code. Let's put in our ROS2 node that will enable us to move the robotic arm using code rather than the command line. So cd ROS2 source, mycobot ROS2, mycobot system tests. Okay, we're in here now. Let's see what we got in here. Make dir scripts. We have a scripts folder. Let's go inside the scripts. Okay. And let's create a new file called get it. Let's do get it arm gripper loop controller.py. So gripper arm gripper loop controller.py. Okay, and what this will do is it'll just control the robotic arm and gripper just to perform repetitive movements between different positions that we specify. So I'll show you this now. So get it. And since I've already written the code, I will just copy and paste from what I already have. System test scripts. Just copy the whole thing. So here is the file. Here's the whole code. All right. Here's the whole code. And I have the whole full code on GitHub right here. It's inside the ROS2 workspace source. It's actually inside the mycobot system test folder, and inside scripts, you'll find the arm gripper loop controller.py. So mycobot ROS2 system test scripts arm gripper loop controller.py. So we now have that in our folder. And what this does, again, it creates a ROS2 node that moves the robotic arm in repetitive motions between a target and a home position. Okay, and the gripper is going to open and close, and the whole movement's going to happen in a loop. And I've got detailed comments throughout the code so you understand what is going on at each phase. So we've got, let's see, up here is where we actually create the node. Okay, here's our constructor. And this line 39 50 through 55, here's the constructor to set everything up. And we've got the action client. Remember, action client is what we want to create using the ARM controller follow joint trajectory action like we did through the command line. And we also want to use this gripper command, this gripper action command action client to call the gripper server so we can open and close the gripper. We want to make sure both servers are up and running. We list our joint names. We have a list for our home position, all zeros, and then our target position, where we want to send each of the 6 joints to, and then a timer, okay? We want to loop through it every 0.1 seconds. All right, and then we've got our method here that will actually send the commands to the robotic arm to move the joints, move the arm, and that's how you do it here using this syntax. We've got our gripper command right here, our gripper command method, which sends the gripper command. All right, that's where we define both the methods. And then this is our control loop callback. Okay, so each time right here, so every 0.1 seconds, this control loop, I'll show you here, that's quick. This control loop callback gets called at this interval of 0.1 seconds. And when that control loop gets called, the code inside this block, this control loop callback, gets executed. And in here, what are we doing? We're moving the arm to the target position. Okay, we're pausing at the target. We then close the gripper, move the arm to the home position, pause at the home position, and then open the gripper, and then a final pause before we repeat the cycle again and again and again. And then we have our main method using the standard way that we do main method for running nodes, where we spin it. Spinning the controller. Yeah, controller, which we made out of an object of type arm gripper loop controller, which we defined up here, okay, in the class above. And then we want to destroy everything, just close everything down when we press Control C. Let's save everything. Okay, we need to update CMakeLists.txt with the new script. So let's go to get it, CMake. Okay, and let's add our file, our new Python file. Okay, first block we need to add is this block. So we need the scripts. I added src as well because later we're going to create a C++ script. So make sure you have this block right here. Now let's add the Python executable right here. Scripts arm gripper loop controller.py. Pause the video and add it right here. This is our Python executable. Okay, now we're save, close out everything. And let's build. Everything built fine. Launch your robot. Be patient while everything loads up. Okay, the logs have stopped, so we know everything is loaded. Now let's open another terminal. And now let's run the node. ROS2 run my cobot system tests. And then arm gripper loop controller.py. We're connected. Okay, and you can see we're going through all the logs, pausing, open gripper, moving target. Let's see if it's actually doing it. And it is. A robotic arm is moving, my friends. Let's expand it out. Turn it so we can see. Doing repetitive motions back and forth. Open, pause, close, come back up to the top. Open gripper, come back down, close, back and forth. I could watch this all day. And let's go over to RViz and take a look. Now, when you're done, go over here and Control C and Control C to close everything down. All right, and let's clear that out. So now let's create the same node in C++, just so you get some experience with that. Let's go over here to SRC, and let's create a program called arm gripper loop controller.cpp. All right. And you're going to go over to the downloads source. Here's our code. Okay, and I'm going to copy all the code from GitHub. Let's close some of this stuff over here. Let's copy, Control A, Control C. Let's go over to our blank and Control V and save. I'm just going to close all that out. All right, and so this does the same thing, just in C++. You can have fun going through it, reading the detailed comments, and you can compare it to it's pretty cool to compare it to the Python script so you can see how the differences in syntax are. You know, C++ is a lot more verbose. To do the same thing in C++, it's a lot more line of code than what you'd write in Python. But have fun going through it. I'm going to save it, close it. Okay. And now we need to update our CMakeLists.txt. Get it, CMakeLists.txt. And we need to add in some new stuff. Okay, that will make this useful so we can actually build the C++ code. So under amint CMake, we're using the RCL CPP library because we're dealing with C++ code now. We're using the C++ action server and working with control messages. So add this block right here and define dependencies. Next, we need to create the executable. Okay, we need to turn that C++ code, that source code, into an executable that can be run when we call it. So I'm going to do arm gripper loop controller, the path to our C++ file, and then the different specific dependencies, okay, for this arm gripper loop controller, which are RCL CPP, RCL CPP action, and control messages library, which will enable us to do the same thing that we did with Python, but we're using different suite of libraries because this is C++ and not Python. Now we need to, now that we created the executables, they need to be installed, and we're going to do that down here. Install CPP executables. Python executables. Okay, everything looking good. So make sure you have the C++ executables. It's in this syntax. Look at it closely. Make sure you got that. So your CMakeLists.txt should look like this now. Control save. Now let's build. Let's go over here and build. See if it builds. Keep our fingers crossed. If it doesn't, have to fix it. Okay, went through smoothly. We always like when it builds fine. All right, and we can close our CMakeList.txt for now. Oh, forgot one other thing. Let's go to package XML, just good practice. Let's update our package XML as well with any packages that we need for this. Let's just take a look. Integration. Yeah, I think we can keep pretty much the same. Everything's good over here. Nothing to update. We'll just keep it as is. It built fine. So now we're ready to actually run. So let's run the robot. Let it come up. Everything stopped. All righty, everything ready to go. Let's move it over. Move it back. Let's expand. Oh, zoomed in too much. Trying to make it nice and good so you can see. Okay, good. So let's open a terminal. Let's run our new C++ code. So we're going to do ROS2 to run the individual node. We do ROS to run. My cobot system tests. And then ARM gripper loop controller. Press enter. Okay, and let's see if it's working. I can see in RViz it's working, doing its repetitive behaviors back and forth. Let's see if it's working Gazebo. Everything working. Hooray. Very nice. Congratulations, my friend. You made it to the end. You made it to the end of this tutorial. You have learned a ton. You have learned how to create everything up from scratch, a complete simulated robotic arm and gazebo from scratch. Thank you for watching. I will see you in the next tutorial. Keep building.